So this is what we have studied before. We have discussed before the introduction for vector functions, the space curve, and how to write a vector function. And then we also defined the limit and continuity. Long story short, what we did is if we want to limit the vector function r, this one, that means we are limiting the components. Okay? So limit of functions f, g, and h. Okay, basically that's what we will do in the vector function. And of course, the continuity is the same, same definitions, same aspect. The difference is we are using it in a vectors. And also some example for how to write and to sketch the vector functions. There are a lot of, I think, examples to observe because the space curve is different from the two dimensions object, right? So the space curve, if you have two dimensions equation in the space curve, you can utilize in and adjusting with the 3D space, which is you can basically rotate your curve, and your curve can be it can be anything actually. Okay, and this is what we have done before. Now we will move forward to, so this is all 13.1. So this is all 13.1. The next terms for 13.2 is derivatives and integrals on vector functions. That's right, just R like that. Okay, maybe I need to write the definition. So this is the derivative. Basically, the definition is the same as we did in calculus 1. So we have limit. And in calculus 1, remember we have h, the gap between the point that we want to observe and to the other point. Okay, in calculus 1, you have this is the definition in the calculus 1, right? So basically the same, similar concept. But now we are looking at the R is a vector function. Okay? As compared with the calculus 1, we only have F on the functions. Okay? In the calculus 1, let's say that's um, the curve, and maybe this is P. Let's just use PQ. Maybe too far, maybe here. Okay, so with the difference is h, what we did is we want to make the h decreasing and becoming 0. Okay, so it's like moving the point Q closer to P, right? Okay. This is the secant line, maybe different color. This is the secant line, secant, right? And the terms gradient or the tangent is when Q is getting closer to P, right? Or we can write the tangent here at this point. Okay, so the tangent will be here. This is just a review for calculus 1. Okay, and this will be your dy over dx, right? You can also look this in more details if you want to look uh, in a triangle, very, very small, and you zoom in that part. This is precisely this. And if you have the angle that, so that you have the tangent is that's why we are calling it a tangent. Aside from a tangible, it's on the curve. Okay. Okay, that's just a review for calculus 1. Now we are trying to applying on the vector functions. Okay, we have the R, the vector functions. Now we can draw in a 3D space. Okay, let's draw here. Say this is, okay, let's say we have the curve C. Okay. Okay. So the same thing we done in calculus 1, we try to make 2 points in this curve. Let's say the P and Q. And this will be the vector positions at P, and this will be the vector positions at Q. Okay. So this will be, let's say this is R T. Okay. The Q will have, this is R T plus H. Okay. So now we include the parametric and directly using it in our vector functions. And now we have the difference here, the secant line. Okay, the secant line here is basically this. The vector functions at Q minus at P. As we are going to observe the limit, imagine you are getting closer, moving the Q, moving to P here. So as we're moving the point, we know that at P, we have exactly this as our tangent. So this is the r prime t. Okay. So basically, we are replicating what we have done in calculus 1, but we are changing the terms into vectors. Okay. So this is the secant, and this is the tangent. Now, because it's a vector, we call it a tangent vector. Okay. Just a few different terms, but basically the concept is similar. Okay. Okay. Now, if we want to look at the r prime in more uh, detail, let's write down the limit of uh, what we have at the first line. Okay. Now let's break down into the component. So let's write this. So if r is so if okay. Now we are using this r into the limit equations. So r prime. To simplify our equations, we write 1 over h at the outside of the whole equations now. Now write in everything with f, g, and h. So f, or maybe I'm just writing all in terms, and you can see uh, the form. Okay. Now, if you limit this whole uh, three components, so we are actually limiting all this limit, limit, and limit. So basically, what we have done here is this is just differentiating each component. Okay. So the first theorem for the derivative. So if you have an f, g, and h, it's supposed to be differentiable. Differentiable. We can write the r prime as just this. Okay. So this is the summary. Okay. Another thing aside from the derivative part is because it's vector, we have also in vector, it's called the unit tangent vector. Or we are usually write down as the capital T. Okay. So the capital T based on vectors is the r prime divided by the value of the r prime. Okay. Now let me give you just a little bit example on how you are using the derivative in this in the factor function. So if okay, if we have that, and we need to find the first derivative, and we need to find the unit tangent vector. Okay. So basically, if you read the questions like this one, find the r prime or find the first derivative, find the derivative, which means we just derive each axis. Okay, derive each axis, and if it's asking the unit tangent vector, we need to divide the r prime divided by the value. Okay, so maybe these questions the unit tangent vector at t equals 0. Okay, so at t equals 0. So we need to find first is the r prime. So from our original equation here is t 3t squared I plus, because it's a product rule, I will write down the final answer here. This is 1 minus t, e minus t, and then j, and then plus 2 cosine 2t k. Okay. And now we are trying to find the r prime at 0. This will be only j and plus 2 k, right? And we can also, if you want to write the value, we can write this as 1 plus 2 squared, square root, and we get square root of 5. So t will be 1 over square root of 5 plus 2. Okay, any questions? I think it's supposed to be not too complicated. What you need to do is to derive each F, G, and H. Okay. And another note, if you have a second derivative, so you have R double prime. This is R prime. Okay. So it's similar to what we have done also in calculus 1. Okay. Okay, let me move to another section. Some notes for derivative. Uh, so some differentiation rule. So let U be its vector differentiable. Differentiable vector functions. And C is scalar, and F is a real value function. We have vector functions U and vector functions V. So basically, you are differentiating each vector's functions. Nothing to be too complicated here. Second, you are multiply with scalar. Then it will be not. It will be the same. Just multiplying the scalar. Scalar is just a scalar. And the third one, if you have a functions and you have also vector functions, you multiply both of them. Now what you can do is you need to apply the product rule. Okay. Now I think from number 4 until 6, it's quite important. This one is, I think you will be able to handle, because here you have the vector, because it's a vector, you can do a dot product here. So dot vector between them. Now, before I'm proving the dot product, let me just write first, and then later I will let you see. So same thing what we have done before. This is also using a product rule, but with dot. So this will be u prime t dot p t plus the number 5 is cross product. It's also similar. It's having cross. But my point here for cross product is if you see the first term is u, then this should be in the first term is u prime u also, okay, because it's a cross product. Number 6, you have functions inside the vector. So it's like a chain rule. So we doing the inside first. We differentiate the inside and then write down the rest. This will be chain rule. This is cross product. This is dot. Okay, for the dot product, let me explain here. So let the vector functions having f1 g1 and h1 as the components, and vector phi as wait, I think we need to make all f. And the second one is g now. If we dot this two, then we will have f1 g1, or let me make complete one. Plus. So we are adding all this, and we can rewrite fg, the multiplication of fg in sum. So we can write like that. So if we have u dot v, and we need to find the first derivative of this dot product, we can do the dot product from this sum. Okay, so let me write this one more time. Okay. Now here you can clearly see you have two functions inside, right? In which you can apply the product rule. Okay. So we can write this sum and then write down the product rule. And this is actually this. And each part of this is actually the dot product, right? This is, we move back to the u and v. So this will be u prime t, u prime dot v, and plus u dot v prime. Okay. You can also do similar things with the cross if you want. Okay. Okay. Any questions before? I think it's not too complicated. Okay. Let me move to other parts. Let me remind you um, if you have an angle between two vectors in chapter 12, you will have, let's say this is two vectors A, B, you have these relations, right? And when your angle is pi over 2, the dot will be 0, which means this is the orthogonal, right? Okay, so from here, actually, if, okay, the value of the vector functions if is a constant, then R prime is orthogonal to R for all t. So if you dot the R, you will get this. And this is a constant. And you find the derivative of the dot product there. So this will be what we have right before. Basically, it's a 2r prime dot r, right? And it's equal 0, okay? Because it's a constant, you derive the constant is 0, right? And because r prime dot r is 0, then r prime is orthogonal to r. And if you want to maybe draw in geometrically, it's like you have a sphere, okay, and you have a helix. And whenever you move on that helix, your vector, let's say if you have the vector position from origin here, so whenever you move this helix part, the vector r will always orthogonal to its tangent. And it's all for derivatives. Okay, so we've done for derivatives here. And my suggestions for the dot product here and the cross product, okay, if we look at here, we have dot and cross. Okay, so my suggestions, but it's up to you also. For dot and cross, um, evaluate dot or cross, then derive. It's just my suggestions to simplify the calculations. Okay, maybe some example here. You have R1, and then calculate. You can try first. So basically what my suggestions suggest to you is you don't really need to break down the formula into the expansions. Okay, you can try from this easy questions. So um, you can expand the dot first, or you can evaluate the dot and then derive. You can see which one is better for you. Both will be uh, same answers. Okay, let's say um, you want to break down this dot product and expand into the product rule here. So let's write this dot. Okay, maybe we can calculate the R1 and R2. So R1 is 2 plus 60 plus 3t squared. Okay. And R2, right, is 4t cubed. Okay. So maybe let's write in terms of 2, 60, 3t squared, and dot the 0, 0 plus. Oh wait, this is t with the power of 4. So from here, this 0 and 0, and we only have 3t6 plus, we have this, right? 46. It's 76, right? Or you can just derive after you dot these two. Which means we have now okay. So basically, for every direct questions like this one, it's 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 probably faster if you dot the equations first and then derive. It will be much faster. But you may need some break down like this expansion if for necessary cases. Like you need to prove something or you need to check whether it's true or not. Depends on the cases. But if you have the direct questions like this one, the second one is probably way faster. Okay. So do not be intimidated by this one. Okay. It seems like really long question, but basically what you are saying here is you can do the dot product here, and then you just take the derivative. Okay, do the cross product here, take the derivative. Okay, I hope that's clear. Okay. Okay, I will go to the next section, the integrals. Okay. So the integrals. So it's also the same as calculus 1. And let me write first the in our definitions of integral in vector functions. So we have integral from a to b dt. Okay. So it's equal limit as n approach infinity of sum. So it's pretty much identical to the calculus 1, right? It's pretty much the same as calculus. This is the calculus 1 here. And this is the a, b, and fx dx. Now you need to exchange all with all f with r, the delta x with delta t. Now if we are going to break down this r into 3 components as we mentioned previously in derivatives, so let's try to break this into 3. So we have f, and let's say this is I, and then the same formula but for g, and this is j, and the last one is k. Okay. So if we are taking all with the same limit, right? So we're limiting here, and limiting this one. So basically what we are doing is this is becoming the integral of a b of f d dt. This is a b dt dt, and this one become a b h d dt. So the conclusions, the summary is maybe bigger. Okay, so basically, it's also similar to the previous concept. So what we did here is we just integrating each component. So integrating R from A to B is integrating the F, integrating the G, integrating the H, all this with the same AB. Okay. So there's nothing too complicated here. Okay. Now we can also use some fundamental theory of calculus. If we have we can write this as the big R, capital R, from A to B, or it's also equal RB minus RA, where the R, this is antiderivative of R. So R prime is R. And that's it, the 13.2. I'll move forwards a little bit to the arc length. Okay, maybe not finishing the arc length, but just an intro for arc length, and maybe I will deliver the midterm results after that. We will have maybe some examples from this derivative later, maybe next Tuesday. I will move to the arc length first. So it's 13.3. So arc length and a curvature. So arc length probably you have learned before, right? So probably you are remember in parametric we have this relations still still fresh, I think, in your mind. So you have these relations, right, in parametric equations in chapter 10. That's the arc length. How about the curvature? The curvature is a new term in these courses, in this chapter. The curvature is actually if arc length is measuring the length, right? So measuring the function's length, right? Curvature is measuring how smooth the curve is. I will tell you like how we are going to proceed with the smoothness of the curve. Okay? But before that, let me just remind you from the arc length first. Okay, so because it's measuring the length. So if we have this, so let me draw the space first. And let's say this is the curve C. So what the arc length means is if you cut the length pieces by pieces, maybe cutting here, here, and then we try to approximate the point with line. So from this one, go here, maybe go there, maybe go there, maybe there. Okay. So you see that if I'm drawing like this, okay, this whole length, the length of the curve, we can approach by adding this, right? Adding this line, right? And this line, we can approximate through our tangent, right? If you remember, we can approach through, let's say this triangle. So we can say we have dy, dx, and dl. Okay? And as I told you before, the way the Pythagoras work is, I think, probably the best way to prove this intuitively, based from your intuitions. So dl will be square root of is dx squared plus dy squared. And you can exchange this based on what you need. Okay, you can use divide by dx or divide by dy. It's also fine, right? But here in the curve here, the 3D space here, we will have three components, right? So let's say we are writing here. So let the R having three components. And then we set the A and B for our integrations endpoint. We can also set the FG in parametric equations, X, Y, and Z. And F prime, G prime, and H prime is all continuous. Okay, so this is also important. So if the curve C traverse or moving, okay? Traverse exactly once. Okay. So if you have loop, then you need to divide by at least 2. Okay. You need to divide. So traverse exactly once as t moves from A to B. And then let me write the L for this 3D first. So it's A, B, and then square root. This is F prime T, and then squared, and then plus G prime T, and then squared, and then plus the H prime, and then dt. Or you can also write in terms of the differentials. So dx over dt plus dy over dt. And we can write this in terms of, because it's plus, 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 and it has square root, we can write this as the value of r prime. Okay, some example, and then we can maybe finish for now. So maybe example here. Find arc length From, let's say, from 300 to 3045. So before you're maybe writing the L equal the formula, you can see the this point, right? So the purpose of this example is to familiarize with the system, okay? Because I believe the calculation for integrations and derivative will be not too much a problem that in those area, but the problem is to, I think, more of to be familiar with the system, okay, with the system. So if you see the point here, and you have these parametric equations, what you need to do is you need to find which t are more applicable in these situations, right? We have 300. So because we have z equal 4t, which means at t equals 0, it will be 0. It's correct, right? So first you need to see any t that possible for this situation. So if t is 0, so x is 3, y is 0, z is 0. So probably t is 0 is correct, okay? And then the other part, you need to see that the z becomes 4 pi. So maybe t is pi. So x is cos pi is negative, so negative 3. Sine will be 0, and z will be 4 pi. So we have t from 0 to pi, right? And that is what we are going to use in our calculations. So 0 pi, and take this square root, and 3 cos and 3 sine will be 9 cos squared, or cos will be derived becoming sine, right? And then squared. And the other way is cos squared t. And then plus 40 becomes 4. 4 squared is 16, right? So this will be 9 plus 16 is 25. So it will be 5. Or this will be 5 pi. Okay. And as a note, we may have more than uh, one function. It can be more than one. So for example, so if t is e with the power of u, then we can also change this into another form. So you may include more than one function inside the whole situations in the vector functions here. So curve node can be okay. I think I will stop right until here. Any questions? No? If no, then the lecture stop here and I will deliver the midterm results. You can check and we will still have time to discuss